Hello, can you guys hear me fine? Great. Hello, everybody. Hello, Krakow. If I'm saying it correctly, shush, Krakow. So, every programming language is built for a purpose, right? Do you guys agree with me? Yes? No? Great. So we should learn from them. Stop fighting for your own language or stop fighting about the languages and start learning from those languages. With that, I'm welcoming you all for the WebAssembly for the masses. I'm Sendil Kumar. This is my Twitter handle. You can reach me out. I'm a developer, and I'm passionate about open source. You can see me contributing to many open source projects. And my sole purpose with open source is to learn things from open source. So what is WebAssembly? Just before going there, how many of you guys are front-end developer here? Front-end? Few? Back-end? Great. Rust? 1. Wow. 2. Great. So what is WebAssembly? Any wild guesses? Come on, speak up. Any wild guesses? What is WebAssembly? No? Have you ever tried WebAssembly before? Anyone? 1? OK, great. So yeah, so we have a computer, machine, or server, which some hardware where you're going to run. And all it understands is like zeros and ones. So all you have to do is like send in zeros and ones. So as a programmer, what we did, in order to make it work, in order to tell it something and make it do that stuff, we just send zeros and ones to it. But it's not so flexible, right? We cannot do everything. We cannot do the memory management. We cannot do everything on top of that. Am I audible now? OK. So we have this entire thing. So what we did was like we built an abstraction layer on top of it, call it as an assembler. And this assembler is where the actual work is done. So we just send in some opcode instructions to the assembler. And the assembler converts that into machine code and runs on the server or machine. But we didn't stop there. We built another layer of abstraction on top of it and sent in some text, which we can understand very freely, or a high-level language, you can say. And we compiled that and then converted that into assembly code or an intermediate representation, and then forwarded that into machine. So that's how the programming has evolved, right? But the problem comes into the picture when you have many machines or different kinds of architectures that come into picture. It's very difficult for us to write something that runs on multiple different architectures. So this abstraction became very much necessary for us to write. And the problem that we are going to solve is the distribution of our applications, right? So you have written your application on one language. You want to distribute it to multiple different architectures. It's very difficult for you to distribute that particular application throughout the world. So you need to have some mechanism in which your application runs on multiple different architectures. And that's a problem as developers we are facing, right? So browsers came into the picture. Anybody can guess what browser is that? It's a very first version of browser created by Sir Tim Berners-Lee. So this is the browsers came, internet just for sharing documents and things like that. Browsers came. And the browsers started evolving. You get to see a lot of different browsers. Netscape came, Opera came, Firefox came, and then we have Google Chrome. Now browsers are the endpoint. Like whatever you're going to do, browsers are one location where you're going to go and check whatever things that you're going to deploy. It makes distribution of your applications much more easier. So how does it work? So browser sits on top of this multiple architecture. So browsers take care of all those conversion of your code into something that runs on multiple different architectures. It just says, give me some code, I'll run it for you, irrespective of the architectures in which I'm going to run. But browsers know only HTML, JavaScript, and CSS. So if you go a little bit deeper, browsers has two engines, like a layout engine and a JavaScript engine. The layout engine is just for presentation stuffs, and JavaScript engine is adding some dynamic stuffs into the entire picture. So that's how it's there, right? Everybody agree with me so far? Yes? No? Yeah, great. And there are a lot of other things that a browser contains, but just to simplify things, we just focus on this two. So what we did, we write something in HTML, CSS, and JavaScript, and gave it to the browsers. Browsers took the HTML and CSS, did the presentation part, and took the JavaScript, run it on JavaScript engine, and added the dynamic part. But JavaScript as a language has been overloaded. It's everywhere. You can write JavaScript applications for IoT devices, cloud consoles. You can write full-fledged IDE with JavaScript. And all those things happen with JavaScript. JavaScript is kind of bloated. It has a lot of other features added to it, which makes it really not a perfect solution for multiple different stuffs that we are doing with JavaScript. For example, running an Electron app in your machine hog up your memory. Everybody experiences that, right? Running an Electron app in your machine. Anybody uses Slack here? OK, phew. So you might experience that stuff. So it doesn't make it very easy for us to develop applications and distribute it together. So what we thought as a community, so we thought, OK, so web is an open system, so we added some other information or some other mode in which we can run the applications inside the browser. And that's where WebAssembly come into picture. So WebAssembly are nothing but a bytecode that you can run on the JavaScript engine, which is built for running JavaScript. But it can also run this bytecode. That's what WebAssembly is. So what is a WebAssembly module? It's a stack machine, a conceptual stack machine. Everybody knows about stacks, right? Yes? Queues and stacks. Everybody knows about them, right? Yeah. So stack machine, but the bytecode that we have is extremely optimized for load and size time dependencies. And it also aims to build the application at a very native speed. So that's a core point of WebAssembly module, to run anything on a native speed, at least near the native speed. That's something that we are fighting as a community for so long time. So how does WebAssembly work? You write in your favorite language, consider C, C++, or anything that actually compiles down to WebAssembly modules. You run it through the compiler, and it generates a bytecode for you. And finally, you can run them on the browsers. That's basically it. But there are only certain languages that have this ability today. But you can go ahead and do this for other languages also. And the spec is continuously evolving, and you can do that later. So we will also see what are the languages that currently supports, and what are the languages in future might support WebAssembly. Great, and it works finally. But any guesses why you need WebAssembly? Definitely it gives us speed, but why do you need WebAssembly? Come on, one answer, apart from speed. So everybody here loves JavaScript, is it? Is there someone who don't love JavaScript? One, two, great. So you need WebAssembly, right? Yes, no? OK, the reasons why we need WebAssembly is it's really fast. It gives you a near native performance. That's what. And it's always not fast. Sometimes WebAssembly code might give you a very low performance. You have to judge your use cases in which you are going to use WebAssembly, because JavaScript is really, really fast. And it's 30% faster than the JavaScript. At times, you can get even more than 30%. At times, you can get much less, like 10 to 15%. So one cool thing that you have to do if you're going to migrate from, if you're going to use a WebAssembly, you have to reduce the boundary crossing. So boundary crossing here means like migrating a data from JavaScript land into the WebAssembly land. You have to try to reduce that. You have to limit the number of times it goes over the boundary, because when it goes over the boundary, it has to recreate everything, which takes a bit of time. That reduces the performance. So these are the two gotchas that you have to watch out for. And again, WebAssembly is also secure, because everything runs inside the sandbox environment. So whatever you run inside of WebAssembly is running inside that sandbox environment. And it follows a linear memory model. You can say that as an advantage as well as a disadvantage, because everything runs in a linear memory model. So you have a single long array in which all the elements are positioned, all the data that you need your application to run or put into. And that makes it really easy to carry data forward, move it further, and use that data somewhere else. But on the other hand, this linear memory model also gives a memory access in your WebAssembly module. So if somebody uses this WebAssembly module and then can read this entire memory that you have in the picture. So that is also one other thing that you have to think over before you are running WebAssembly. The WebAssembly module is portable, which means like you can use that effectively across platforms. You have multiple different architectures. You can use this WebAssembly module across those architectures. One other thing is, how many of you debugged JavaScript performance? 1, 2, 3, 4. OK, great. How many of you liked that experience? Like, nobody? Okay. How many of you still using IE6? One? Wow, we should meet after the talk. So JavaScript gives you a consistent performance. JavaScript doesn't give you a consistent performance, and it differs based on the engine in which it's running. And it strongly depends on the browser in which it's running, also certain environment factors. But what WebAssembly tries to provide here is like to give a consistent performance across all formats. It also tries to give a maintainable performance. So maintainable performance here means like you can write your code in your language, which is you are so strong about. And also, it's very helpful for you to understand this entire language. And most of the languages are typed language, which means you don't have this runtime exceptions and things like that. You can optimize them further, but the code looks maintainable. But in other case, if you're writing your JavaScript and then trying to get maximum performance out of the JavaScript, it will be really hard for you to follow what is happening. Because JavaScript, you can even write a geeky JavaScript that kind of nobody understands. But what WebAssembly provides you is like giving a maintainable performance. And it also has multi-language support. You can bring in any of your language and then try to run it on WebAssembly module, which means in browser you can run different languages. So JavaScript, what's about JavaScript? JavaScript is easy, right? Everybody agreed to that fact, right? It's easy, it's not typed, it's very easy and concise to write JavaScript, and there is a reason that it's the top of the list for 5 years in a row. So we have to agree. And we also have a new entrant around 2017, TypeScript, which moved to 7th place straight away. It's all because of JavaScript. So you can combine them together and find that as a JavaScript, call that as a JavaScript. So it's really easy. That's why billions of developers do JavaScript. And you can do something like this. In JavaScript, as you can see here, this particular stuff, you don't have 3-dot operators in JavaScript. This is something exclusive on some of the languages like Rust. But we don't have this thing here. But we can actually implement that feature with just 4 lines of code. And this actually prints 0 to 10. So that's what you can do. The flexibility of JavaScript is really great, which means like you can do all sorts of things with JavaScript. But it's weird too. How many of you agree with that? Everybody? Hey. OK. So let's see how weird it is. So I have a sample application here. And hopefully the demos works. So it's nothing. It's a simple HTML file with vanilla JavaScript. I have some weird syntaxes and try to call those weird syntaxes and see what is going to happen. So let me go ahead and run this thing. OK, so I have 5 things. The first one, is everything visible? Is it fine? Yeah. So what do you think the output of the first one? How many of you think it will be false or NaN, not a number? How many of you think it's not a number? Nobody? How many of you think it's an array? 1. How many of you think it's an object? 3, 4, OK. So the answer is object. It's just an object. So with that knowledge, can you guys guess what's the value of this one? How many of you think object? Not a number? 1, OK. Not a number? 1, OK. It's not a number. Fine. This syntax, how many of you think what's the value of this one? It's very simple, right? Syntax error. Nobody? 1? 0? No guesses? The answer is 1. It's because this guy is an object, and you concatenate that with a plus. It converts into a number, and it's a false, so it becomes 0. And you're putting a not on top of it, so not of 0 is 1. OK, this is very cool. The last one, like the function, how many of you know what it evaluates to? Guesses? OK, 0, 1, 1. Nobody? OK. Not a number? No? The answer is 1. Because the function evaluates to 0, and you put a tilde and a negative sign, that evaluates to 1. So I'm grouping this function together here. I'm just concatenating all this function, and the answer is 42. So I can get a number out of this thing. And there is also a weird syntax that I was seeing. Hopefully it's there somewhere. Yeah. So can you guys see this thing? So what do you think this will evaluate to? Guesses? It actually evaluates into a string. It converts into a strange thing. And you can do a lot of things like this in JavaScript. It has that flexibility there. Let me quickly stop this and go inside here. So what do you think the output will be here? 0. It's a plain XOR operation. You're XORing two same numbers. 1? No. The value is 0. But what you can do is you can check whether it's a 0. It gives you this value. But you can do that. It gives you true. Any guesses? Yes, operator precedence. Exactly. So you can do all sort of weird things with JavaScript. But as a language, it's the most lovable language. It's very easy for you to get started, very easy, and enables billions of programmers to write the language. But you do have this kind of sweet spots you can call if you want to. So let me go back to the slides. But how does JavaScript work inside the browser? Anybody knows how does it work inside the browser here? Huh? OK, sorry? Of course, you should know, right, if you're writing JavaScript? Great. So you have this plain HTML file. Your browser just goes to this index.html, and it finds, OK, I have a JavaScript link there. And then it goes and checks, oh, wow, OK, so this JavaScript has this kind of dependencies, A, B, C, D, E, and F. It can be a cyclic, too. So all those dependencies, so what the browser will do is initiate the request to the base URL for those files. It goes ahead and fetches all those information. It downloads everything. So you have to note that the entire JavaScript and its dependencies should be downloaded at first. Once it is downloaded, then it parses this thing. The parse will give you an AST, or abstract syntax tree, with which JavaScript is an interpreted language too, which means this ASTs will be interpreted, converted into bytecodes, and this bytecode will be executed. On the other hand, you have something called profiler or a watcher that sits there and watches for the executing functions or interpreted functions. It checks for those interpreted functions and says, OK, so this guy is getting called more number of times. So what we can do is OK, we can optimize this guy a little bit. So what we have is a compiler. This compiler kind of optimizes the code and produces a bytecode. And this bytecode will be executed. So the output of this execution will be much faster than compared to the output of the interpreted execution. But if you're calling a function again and again, JavaScript tries to optimize. Here, optimization basically involves assumption. Assumption in terms of type, assumption in terms of where the values will be located, things like that. So it assumes that this is going to be integer always, and then it goes and optimizes it further, reduces a compact source code, compacts bytecode, and uses that to run this application, and it runs much more faster. So this is the fastest JavaScript that you can get running on the browser. So everything will be executed. So this happens. And obviously, you spend a time on compilation. You spend a time on optimization, right? And finally, you have this garbage collection that happens entirely. So this is how the execution of JavaScript looks like inside your JavaScript engine. On the other hand, the WebAssembly is much simple. You can load a WebAssembly like this. Just fetch a WebAssembly module, which is .wasm file, which is nothing but a binary. You get the response. You instantiate a WebAssembly module in it, and then run the value with that stuff. Bunch of promises. What you can also do is instantiate streaming. Instantiate streaming is on the go. If you're downloading 100 KB of WebAssembly module, at the very moment you get the first byte of information that will be compiled and then instantiated. So that's what's going to happen. So instantiate streaming is something that you can do, which helps you to fasten up the WebAssembly execution even further. That's the awesome thing about instantiate streaming. So how does it execute inside a browser? So you get the fetch. So the fetch code here, this fetch code here, fetch simple wasm. This code goes and gets an element, gets a WebAssembly file. And once it is downloaded, it goes ahead and decodes the particular file. So the WebAssembly module is basically encoded. It decodes a file. Once it decodes, you have this binary information. You just have to compile it further. Any guesses why this compilation is required? Basically, WebAssembly module is already compiled, right? It's a compiled bytecode. So why do we have to have a compilation here? Guesses? No? 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 OK. The compilation here basically converts the optimized and compiled bytecode into something that works on the architecture in which the browser is running. So that's the compilation happening here, which is much faster. And finally, it can execute this entire bytecode information. That's what is happening inside of WebAssembly execution. So as you can see, the JavaScript execution has multiple steps. On the other hand, the WebAssembly execution has only 3 steps, which makes it really faster. Parsing is a huge job for a JavaScript engine to do. It hogs up a lot of memory. It hogs up a lot of time to do this parsing. But decoding is very simple to do. You can do it in nanoseconds. On the other hand, compiling and optimizing happens inside the JavaScript engine. Is really bigger, and it spends a lot of time to do that stuff. But the code that comes out of WebAssembly has this compilation inbuilt inside it. So the WebAssembly code is already compiled and optimized, which means it can run much faster. This compilation step is also shorter. And finally, the evaluation or the execution is also shorter. So which language supports WebAssembly now? Any guesses? JavaScript? No. C, yes. JavaScript cannot support WebAssembly because it needs type information, and JavaScript doesn't have type information in it. Sorry? Rust, yay, OK. Sorry? Java, I don't think there is an official support for WebAssembly. I think there are some experiments going on for Java. Any Kotlin fans here? Nobody? Nobody likes Kotlin here? OK. Kotlin native has this WebAssembly. So basically, you have C and C++. They gave the best performance, as usual, because it's C and C++. But who is going to write C and C++ again? So it's C and C++. That's a big disadvantage. And its mscripton is the tool chain that kind of converts the C and C++ code into the WebAssembly modules. And it's a very first tool chain, and all the other tool chains actually rely on mscripton's advancements. So it is the best tool chain that you can get. But when you're writing C and C++, it's a basic thing that you have to write a lot of verbose stuff. You have to write a lot of code in order to convert this entire stuff into working WebAssembly modules. That is a pain when you're doing it. On the other hand, Rust is the best tool chain available at this moment. Performance needs to be slightly tuned. You have a better performance, but we can even tune it further. And it's integrated within the language, which means like you can write a normal Rust code, which is a normal Rust library, which is used for system programming, and you can straight away convert that into WebAssembly module without much fuss. It's really easy and straightforward to do it. And that's the good thing that you can get when you're building a language very newly, and also building a language that has a native WebAssembly integration. You can also compile TypeScript into WebAssembly modules. AssemblyScript is a project that's out there, which kind of converts your TypeScript into WebAssembly. It's insanely fast and easy to get started and get running. And you can just go ahead and try. If you love TypeScript, you will love this experience. And also, there's a lot of other languages like Go, Kotlin native, and Swift have much like experimental or beta-sized WebAssembly support. And I think in future, there will be a lot of other languages get added to the list. So let's go ahead and run a couple of examples, how you can do a lot of things, how the performance is better. And then we'll come back to the slides. Any questions so far? No? Great. So it is a basic Rust project that I've created. And as you can see here, it has cargo.toml, which is a package JSON or a dependency manager for the Rust application. And all I have is a WASM binding here. And this is visible, my editor visible for everybody up there. Great. So it has a WASM binding, which is a tool that helps you to convert your WebAssembly modules and create a binding files. And I will come back why we need some binding files. And this is my source. And as you can see, it has nothing. It's just a simple Rust function with a greet that gets in a name, and that calls an alert, and it just passes in a string to it. And this alert, I'm extending it, which means I'm exporting that alert to the outside world. So that's how it is there. And I have a package JSON file, which has nothing but few dependencies for running WebAssembly, something like Webpack. Anybody knows about Webpack here? Yeah, a few of them. So it has a Webpack, and it also has some polyfills like text encoding and things like that. And I have 2 scripts with which I'm going to run the application. And all I have to do is like import the particular Rust package or the bundle that comes out of the Rust. And then I'm running, this gives me a promise. And I'm just evaluating that promise and get the value. So that's what's going to happen. So let me go ahead and run npm run serve. So it boots up the server, and then my server is running on the localhost 8080. As you can see, it just gives me an alert stating hello world. I cannot zoom in. OK. So it just gives me an hello world, and it says hello world. That's it. So that's very simple application. So the advantages of having this inbuilt in the language is just adding this annotation will help you to compile a Rust code and run it on a browser as a native module inside the browser. So that's an advantage that you have. So let's go and check the performance. We have been talking a lot about performance, how good the performance of WebAssembly is. Reminder, the WebAssembly is still in its beta. I mean, still in just the version 1 is released. And you might have a much better performance improvements. But now, let's see what is happening inside there. So what do I have here? I just have a single C file, which creates a Fibonacci number. I think everybody knows about the Fibonacci number, right? Just creates a Fibonacci number or the nth Fibonacci number. And what I'm trying to do is like run that particular stuff for 1,000 times. That's it. So run a Fibonacci series for 1,000 times for a given number. That's it. That's what I'm doing inside the C++ or C. And again, this is a plain, simple HTML file. And here you can see some things that I've done here just to show the Sentia value in the browser, which might not look nice, but some basic HTML stuff. And all I'm doing is like importing something and then running this application. That's it. So how do I convert this code? What do I have to do in order to do this thing? I have to first set up a tool chain, which is mscripton. I have to set up that tool chain. Once I have the tool chain enabled, then I can go and convert this WebAssembly code that I have and run and convert them into a WASM file, and it creates a binding file for me. And this binding file is something which helps you to transfer data from WebAssembly module to the JavaScript world, and also JavaScript world to the WebAssembly module. So it does all those things. So let me go ahead. First, I have to set up I have this mscripton SDK available here. All I have to do is like source emSDK environment. This sets up my source environment, and emcc will be available for me. That is an mscripton compiler. Let me go back here. Let me come to where's this project? Oh, good. It should be on Devoxx. No. OK, it should be on demos, Devoxx, performance sample. So I have this here, and all I have to do is like emcc, an optimization flag of 3, which gives a much faster performance than compared with optimization 1 or a default loading. This is basic C building or C compiling. And then I'm specifying build me a WASM file, WASM equals to 1, and also export a Savewrap function, which kind of creates a wrapper around the function that you have, and then gives me back the particular file or particular function that I have to call. So I just run this. And this creates me this huge chunk of text. This basically, what does it do is like it emulates a file system, and then it kind of loads this entire application and uses that application. It also exports a function that I have it here. How do I export a function? Using this mscript and keep alive. And this annotation is coming from this library, mscript.h. So I can go here and see. So once I've done this, I just loaded this JavaScript file that is generated. And once a runtime is initialized, so it creates its own runtime, its own module. So once it is initialized, I'm just going and calling the Savewrap. Savewrap is a function that I've exported here. Savewrap is a function that I've exported. So this runtime method will actually get have a list of functions that I have in my C-lang file. It just goes ahead and calls this function. I'm saying, OK, so call me this fifth function, which takes in a number and returns a number. And this gives me a value of 40. And then I'm running it for 1,000 times, so I'm just calling this run 1,000 times function. And then I'm checking performance, start of the value and the end value, and then I'm returning the difference of those things. And once I have the difference of those things, I just run this entire thing and then prints that output in the file. So that's it. And I have another file, fib.js, which is nothing but JavaScript version of this Fibonacci series, and it has run 1,000 times and all those things values. And I'm also printing this entire thing here. So let me go ahead and run this thing. Not here. What happened? Yes. So as you can see here, it also prints me the value of this 40th Fibonacci number, which is this. So as you can see here, the JavaScript version runs in 0.23 milliseconds, while the WebAssembly version runs in 0.1 millisecond, which is faster. But this gets even more further, or sometimes it will be much more lesser. I mean, JavaScript version which will be much more lesser than compared with WebAssembly. That's because of all the shenanigans that we have here. That is this JavaScript file, the huge JavaScript file that we have here, will cause this values to differ a little bit. But most of the time, it lives in the time frame between 6 and 12 or 13 or 15, something like that. Sometimes JavaScript will be much more faster. And what would be really interesting is like when you run this inside a loop, for example, you're running this inside a loop and getting more and more loops, like you added like 1,000, you have 1,000, you increase that to 10,000 or a 1 million, things like that. Then what happens is like JavaScript is much more optimized than compared with WebAssembly stuff. Because in WebAssembly, the compilation, once you get started, the compiled code runs much faster for the lower number of loops. But on the other hand, JavaScript, when you have higher number of loops, JavaScript stands out because it compiles and optimizes and does all sort of things to go there. So that's where you can take a decision of how to use it, where to use JavaScript and a WebAssembly. Yes? Yes, so you can have access to all this custom C code that you have. There was like a couple of amazing articles from Das Arma from Google, how to compile your own C language library into WebAssembly modules. So you can do that sort of thing. So you can always try to convert that everything into WebAssembly module. The one thing that you cannot do pretty much good is using complete standard functions or doing an OS kernel calls. That kind of libraries is not capable of converting into WebAssembly modules now. And we have a separate thing called WebAssembly System Interface, which kind of does that for you. But you can take any C code and try to convert into WebAssembly module and use that in your application for now. Yes, it will be compiled and deployed. That's what basically we have done it here. So as you can see here, I just tried to compile this WebAssembly C code, Fibonacci, which is a C function that I have. I just tried to compile this function using MCC. MCC is a compiler. So you compile this thing, convert a bytecode. So I will have a bytecode here. a.out.wasm is the bytecode for me. So I can also see that thing here. So you can see like this is a much smaller WebAssembly module. So I can see what happens inside. This is an entire Fibonacci loop convert it into binary. So you can use this binary inside your application. So that's how you can do. So you have to compile it first. And when you're compiling, you optimize it using O3 and things like that. And once you're optimized, you have this chunk of code, binary code. You can run this binary code straight away in the browser. Get it? Yes, it's a static compilation. Sorry? It is secure because it runs in the same sandbox environment just like JavaScript. JavaScript is running on a sandbox environment. This also runs in the same sandbox environment. You cannot have access to the external world. Whatever you want to do, you have to send the information to that module and use that module as a sandboxed code that runs inside that entire sandboxing. So it's very secure than compared with other stuffs. Question was there. There was this question there. Yes? Sorry? Yes, there is a difference between JavaScript engine and the browser. That's basically how it has been implemented, the JavaScript engine, how it was implemented. Because sometimes you could see Firefox Developer Edition or Firefox have a much better performance than compared with Chrome for a bigger WebAssembly modules and things like that. For a smaller stuffs, it's more or less the same. But for a bigger stuffs, bigger WebAssembly module and bigger things, Firefox has a little bit higher average than compared with Chrome. That's basically how this entire engine is built. And Firefox, since they started with this WebAssembly stuff, it has been like pioneered with a much faster boot up performance and things like that. No, the things that we compile now is applicable for all the browsers. It doesn't matter which browser you're running. OK, and there is one more example. So basically, this is another example. Let me open this here. This basically creates paint inside the browser with WebAssembly. So how does it look like? It's just built in Rust. You have this cargo terminal. The other dependency that we have is like WebSys. And WebSys is using for web APIs with the WebAssembly modules. And you can write a web API kind of thing inside the Rust itself using this library. And I'm just using this kind of elements there, the document, element, event, target that we use inside a Rust file. So as you can see here, you have a start function inside which I'm just calling a window object and getting that window object, creating a canvas element inside it, and setting all the canvas properties. And I'm trying to emulate this entire thing. So if you go back there, my application is running there. So let me go to 8080. So this is a simple paint kind of an application where you can write something. So this is also possible with WebAssembly at this moment using Rust and WebAssembly. You can do this entire thing on C++2 or C2, but the amount of code that you're going to write is very verbose. And also, you have to create your own WebIDL interfaces, which is a pain to create. But as an ecosystem, as a tool chain, Rust has this things built inside it, which means like you can just go ahead and use those libraries, and that libraries provide all the gelling between the files that we have in WebAssembly module, or the function calls that we have in WebAssembly module, and in the JavaScript or the browser world. So you can see here, this is the output generated by the Rust builder. And what happens basically here is like you have this JavaScript file. So this JavaScript file uses all those things that you need to have. You can get a memory object. You can drop a memory object. You can take an object and use that. You can get that memory access because the memory is a shared array buffer, so you can take the memory access. You can even do all sort of things. This is a binding things that has been generated. So calling a canvas inside your WebAssembly module will come and call this function, and this function go ahead and call the browser API, or the document API, or the JavaScript API, and things like that. So this is how this entire thing is structured. So you have a binding file that kind of converts everything from the WebAssembly land into the JavaScript land. But think before using it. WebAssembly is still in its very early stages. And this is something that we have in assembly script FAQ. You can just go ahead and see this thing. If you want to do some compute-heavy stuff, just use WebAssembly. It helps you there. But if you want to have a lot of DOM access, just like the paint example that we've seen before, don't use WebAssembly there, because we don't have that much clearer APIs, and you always end up in having much slower performance, which with JavaScript, you can achieve even better performance. So think before using it, where you have to use it, and how you have to use it. And also, one more thing is like the boundary crossing that we have discussed. Like traveling from JavaScript to WebAssembly land, you have to make sure that you're doing that minimal number of time. If you increase the number of time this boundary crossing happens, your performance will obviously go down. That's the bigger problem. So what happens? What is in the future of WebAssembly? At this moment, the JavaScript and WebAssembly actually sends only numbers. So WebAssembly accepts only numbers from JavaScript world. You cannot send anything else. And there is a proposal that we have now, which is a reference type proposal. And this RFC is available in the GitHub. And what it does is like, I can send any JavaScript object from JavaScript land into the WebAssembly land. Currently, you cannot do it. But how did we able to achieve those interfaces? How did we able to use strings from JavaScript to WebAssembly, or WebAssembly to the hello world example that you've seen? We have paused a string from the WebAssembly into the JavaScript, right? How did we do it? Any guesses based on the things that we have said before? Come on. No guesses? OK, so we have the shared array buffer. We just send them the pointer of the shared array buffer and the length of about which you have to get the value, and uses those two information to fetch the information from the WebAssembly land and put it in the JavaScript land. That's how it happens. So there is obviously a glue code. There is a host binding proposal that is happening, which kind of removes this glue code out of the picture, and you can just use JavaScript and WebAssembly together, just like normal two JavaScript files. And garbage collection is not in the language spec anywhere. It's not added. There is basically a discussion going on, because languages like Java or some other language that might come in the future might have their own garbage collection, which is tested, which is so robust. And do we have to allow them to use the garbage collection inside WebAssembly, or create our own garbage collection? So this is the discussion that is happening. But garbage collection, you can expect that in the future, at least a decision. And there are awesome things like Cloudflare Workers or some other workers that we have, which kind of have a worker which runs on your remote system. You can just use it. It boots faster, and you can run your functions much faster inside there. And last thing to mention is like you have something like WASI, which is WebAssembly System Interface, which makes your application to run as a native application in your computer or a desktop or the laptop, things like that. So you can generate an application for running for that runtime, and then use that, deploy that application anywhere. So that is also some of the interesting things happening. And WASI is actually built on top of some conceptualized system, and you just provide that conceptualized system via runtime. Questions? We have 5 minutes more, so any questions? Yes.
The first question is, I have 2 questions.
Yes.
You said that WebAssembly doesn't optimize itself. How does it come that in your example?
Sorry?
Like in your example you showed, the second and the third call, they were faster than the first one. What does it come? Because you said that WebAssembly doesn't optimize itself.
Yes, that's a good question, but WebAssembly doesn't optimize itself. In sense, like the code that you're generating is already optimized. Just-in-time compilation that happens inside the JavaScript engine will not happen for the WebAssembly now. The difference that you have seen when you're running or refreshing is basically because of the JavaScript engine that's happening there. Sometimes it executes much faster, sometimes it executes much slower. That's the basic reason that you have seen. What was your second question? Okay, that's a good question. By default, JavaScript doesn't have access to your file system in the browser. So it cannot go and load something from your system and then show it, because that's a big security loophole in your system then. So it doesn't have that capability. And also, WebAssembly doesn't allow you to do that because it doesn't have that feature enabled. And the sandbox inside which it runs doesn't have any APIs that calls to the system calls. So there is no way that you can do it. But what you can achieve with VASI is you can create that capability inside a native module using a runtime. So how VASI works is like you give it a description that you have access to this particular directory, and it goes ahead and creates something inside the directory, or deletes something inside the directory, or fetch something inside the directory. Then you can have the system calls interface enabled. But it's very, very highly in a beta version. So if you want, you can give it a try. Thanks. There was a question here.
So is there a case for running WebAssembly without the browser, outside the browser?
That's VASI and Node. Node also supports WebAssembly from its version 8. So these are the two use cases that you have, something outside the browser. And basically, you have some libraries like Node.js, or some libraries where you have to use your native modules. Like Node.js is a library where you have to compile C++ and use that compiled code somewhere. For those use cases, you can just remove that particular stuff and use Wasm there. If you have used Atom, Atom is a Node Electron-based application, right? So what Atom does is like it has a lot of search. For example, you're doing some search. It goes ahead and uses C++ APIs to have a better, faster results. What they can do now is like remove that entire code away and then use a WebAssembly module there, which kind of reduces and gives the flexibility for the code that is running somewhere else. So those are the use cases that you can think of. Any more questions? OK, thank you for your time.